Hey, good morning and good afternoon and good evening to all of our viewers globally. And welcome to this webinar brought to you by the Oil and Gas Special Interest Group of the Institute of Marine Engineering, Science and Technology, the IMarEST. My name is Paul Jukes and I'm the Honorary Secretary for the Gulf Coast Branch and Committee Member for the Oil and Gas SIG based in Houston, and I'll be your moderator for today. It is the privilege of the IMarEST SIG to host Xiaojiang Long, a Senior Principal Engineer from Fugro, on the topic entitled Case Studies of Geotechnical Challenges in Marine Geotechnical Engineering. Dr. Long is the Senior Principal Engineer and Technical Authority for Fugro USA, based in Houston, Texas. She has over 18 years of consultancy and management experience, specializing in marine site characterization, foundation design, and well geotechnical and interdisciplinary geohazard assessments. Dr. Yang Long has obtained a master's degree from Tongji University in China and the Doctor of Philosophy in Texas A&M University in College Station, Texas. She's a registered PE engineer and a board-certified geotechnical engineer by the Academy of Geoprofessionals. She's published over 35 technical papers and is the serving honorary secretary of the SUT, a US Executive Branch Committee. She's one of the finalists for the Ground Engineering Magazine 2025 Inspiring Women in Construction and Engineering Awards in the category of Technical Excellence. And she's also a member of the SUT Oil and Gas SIG, as well as the International Society of Soil Mechanics and Geotechnical Engineering. So just before we start the presentation, you'll see Slido. There'll be a link for Slido. So if you do have any questions, this webinar will be muted, but please submit your questions to the Slido box that's with the link that's been provided, and we'll take the questions at the end of the presentation. So that being said, I'll now hand it over to Dr. Long for her presentation.
Thank you, Paul, for the kind introduction, and also thank you for the opportunity to present these case studies. So typically, for marine geotechnical engineer, need to require a blend of technical expertise, analytical skill, and also communication abilities to handle the unique challenges in marine environment. This slide shows some kind of typical examples of what we do for marine geotechnical engineering consultancy. Here we will mainly focus on 4 case studies to explore some kind of particular challenges we deal in marine geotechnical engineering consultancy. Some of them are not even classified as typical geotechnical engineering problems. So first example is the spudcan-suction bucket interaction analysis. So here, the client wanted to install a jack-up unit near a platform supported with a tripod suction bucket foundation. So due to the site condition constraint, the closest distance of the spudcan edge to suction bucket edge distance is about 1 diameter of the spudcan, one times of the spudcan diameter, which is at the borderline of this, the ABS, the standard, whether there will be significant kind of a spudcan nearby facility interaction effect. So the client has entailed us to perform kind of a numerical simulation to evaluate. So first the question is whether the spudcan operation is going to cause the significant kind of the spudcan suction bucket interaction effect or not. Second, if there is an interaction effect, in terms of geotechnical foundation performance, from the aspect of stiffness and holding capacity, how much reduction we need to consider whether they're going to cause a problem with like the spudcan tripod foundation like stability or not. So given this kind of like the scope of work or objective, a suite of Abacus three-dimensional finite element analysis were performed. So like we used like the Abacus coupled Eulerian Lagrangian large deformation finite element spudcan penetration analysis, followed with Abacus small strain finite element analysis to assess what's the difference of the suction bucket holding capacity and also the stiffness before the spudcan penetration, and also what are the difference like after spudcan penetration, like full insertion and extraction, what's the reduction, what's the difference like in terms of the capacity, factor of safety, and also the initial linear stiffness matrix values. So here like shows like the suction bucket stiffness matrix is a mathematical representation of suction bucket resistance to applied design loads. So it's typically modeled as a 6x6 matrix. So this stiffness matrix quantify how much spudcan deforms under different loading conditions such as vertical, horizontal loads and moments and the torsion loads. So for like the suction bucket holding capacity analysis, it's very important to note the bucket holding capacity are load path dependent. So in other words, the vertical holding capacity of the bucket is influenced by the existence of the horizontal force moment torsion and vice versa. And also like as a tripod, like the bucket foundation, the bedding capacity is also influenced by the bucket spacing, embedment depth, soil properties, and also sort of like the suction bucket group effect. So for the Abacus CEL large displacement, like the finite element analysis, basically like the soil portion is modeled as the Eulerian part with the finite element mesh stationary, while the material is allowed to move independent of the mesh from element to element. The structure, the spudcan and the suction pile is simulated as this traditional Lagrangian part. So basically here just showing some image of like the Abacus CEL, the spudcan like the continuous penetration process. So for the spudcan bucket induction analysis, it's very important to simulate the creation of the soil crate and also the soil disturbance, like due to the spudcan operation process. The progressive, like the strength degradation, like in the study, is accounted based on the Abacus CEL, like the large deformation finite element, spudcan penetration, the removal analysis. So this one showing basically a typical guideline, like specified in the ABS, like the standard guideline for the spudcan penetration. So typically, so this one like identify like for the clay layers, like due to the spudcan penetration and the removal for the footprint, what are the range of the soil disturbance influence zone? Okay, so the next topic move to the stability of the production wells in gas hydrate bearing sediments. Gas hydrate, it's like a very common like the geohazard. We typically like encountered like we can typically see like in like the deep water environment. So the gas hydrate are composed of the gas molecules trapped in a solid ice-like water molecule lattice. So the gas hydrate, the dissociation, or we can also call that the hydrate melting, it's referring to a phase transition of the solid hydrate into gas and the liquid water due to altered environmental condition change, such as increasing temperature, decreasing pressure, or injection of chemical inhibition. So as a hydrate, like the dissociation when the process as a geohazard, it can cause the problems such as like the seafloor heave or subsidence. For the foundation, like losing the holding capacity and causing the instability of the well casing. Also, like it can cause like the slope stability or submarine sliding failure. So one of the famous example is this like Orman Langer, like a Storga slide in Norwegian Shelf due to like the gas hydrate dissociation. The excess pore pressure, like the increase, reduce the vertical effective stress and then causing the slope instability. So for this study here, we performed a sequential numeric modeling scheme to assess the wellbore stability during the production due to hydrate dissociation effect. So in this like the numeric scheme, like the sequentially coupled analysis, like the starts with the heat transfer analysis, followed by sediment fracture propagation assessment, sediment motion prediction, and ended with like the wellbore soil interaction modeling. So first, like for the heat transfer process, the gas hydrate dissociation is an endothermic process. The progression of the dissociation front, also and also the volume of the hydrate dissociation is a function of the nature of the hydrate habitat, thermal properties of the soil surrounding the production well, and also the well components like the thermal conductivities, the formation temperature and the pressure level, also the details of the produced hydrocarbon, such as the production flow rate, well temperature profile, production time profile, also the well layout. So in this desktop study, like basically like the two types of the gas hydrate exist in the field. So we have like the type 1 biogenic gas hydrate followed with the thermogenic hydrate like below about 180 meter. The whole gas hydrate stability zone is about 340 meter below mudline. The gas hydrate concentration, like the values from 5% to over 20%. So for the started like the well site, basically we have like the 36-inch surface conductor followed with 20-inch surface casing. So considering that this gas hydrate dissociation effect, the basically pretty strong steel like the X80 API steel and the X80 and the X56 like the steel were considered for the surface conductor and also surface casing. So first we employed the two-dimensional heat transfer modeling. So from the modeling, we can evaluate the hydrate saturation and the temperature contours after like the specific target years of well production. And we can also assess the profiles of hydrate dissociation front with time, and also how much volume of the gas hydrate going to like dissociate. So one thing we didn't mention in the previous slide. So after gas hydrate dissociation, like the volume going to be like expanded. So basically 1 cubic meter of like the solid gas hydrate after it dissociated with the creation of the gas and the water, the volume going to be expanded to about 2.3 times of the initial volume. So basically like the volume entrapped in the soil after the hydrate dissociation going to be much bigger than than the solid hydrate case. So considering the uncertainty of the in situ stress state and also past the geological history, the stress state change after the gas hydrate dissociation. So two scenarios were considered to bound the assessment of the sediment fracture propagation. So first case, we consider if there is no direct channel for the dissociated gas migrate to the sea floor, then basically like this expanded volume can only kind of like displace in a horizontal direction. So basically, so this scenario we call the non-venting horizontal fracture field. And also another like the scenario is like could possible in the field is if there is kind of like a continuous channel existing to allow the gas evaporate kind of from the sediment to the sea floor. And then with this gas, like the migration, the subsidence is going to be experienced for this vertical venting fracture field. So basically, this like a non-venting or venting, like this kind of scenario, like a horizontal non-venting, vertical venting, like this fracture propagation, like the scenario going to cause like the dissociation induce the soil motion. So here the soil like the effect is different from traditional like a foundation like a soil to support the load. Here like this like the soil motion will transfer the loads to the structure element. So when the soil move, it's going to impose the loading condition on the structure element here, like will cause load on the producing well. So this well soil interaction like arising during the hydrate dissociation, it's a function of the well design, well installation procedure, and also the dissociation effects on the soil properties. To simulate this like the well-bore soil interaction like effect, we have utilized the two-dimensional finite difference computer program FLAC 2D by Itasca to model the well response due to the hydrate-induced the soil movement. So in the model, the soil stiffness change as a function of like the soil motion, like the soil strength, it's incorporated in the numerical analysis. So this one showing the example of the soil motion profile, the well vertical motion profile, and also the well stress, kind of like the axial stress like a profile. So here, as we can see, basically, even after 2 years of the well production, at like the 300 meter below mudline depths, like we actually we have seen like the significant like well casing overstress. So basically, like it could potentially cause the problem, instability problem with the well casing. So in the design, we need to incorporate this factor. So the third example is the assessment of the sea floor stability and the foundation performance under well action. So this study is specifically for the hurricane wave and the sea floor failure at the U.S. Mississippi Delta region. So at the Mississippi Delta region, due to the rapid deposition along the delta form, like it's actually a significant thickness of very weak sediments was formed at the subsea soils. So these very weak soils are kind of like marginally stable at the best, and the seafloor failure can be easily triggered by the hurricane waves. So the basically like this map showing like the contours of the region of the mud flow gully, kind of like and also the region of the mud flow lobes. The gully mud flows are triggered by the typical wave like of the small to mediums, like the to large hurricanes. So which causing the pressure on the sea floor. The wave pattern, like the pressure, generate the sea floor failure in shallow and deep water on the delta front. The induction of the surface wave and the seabed is a complex dynamic problem. So we need to consider the nonlinear soil with elastic behavior. We need to consider the energy transfer between the wave and the moving soil. And also this kind of oscillatory like motion caused by the surface wave. So like due to the wave, like wave pattern, like the pressure, considerable sub-bottom movement and or submarine landslides are observed even with a slight slope, like even when the slope was only like 1 or 2 degrees. So for the hurricane waves, so we say, as we know, like the wave size increase with the intensity of the storm. So the large storm wave typically like start arriving hours, like hours or even days before the center of the storm. So this one like showing example of the storm wave triggered the seafloor failure and also causing the facility failure. So for the SP-70 platform in Mississippi Delta region, like basically the platform was toppled in the hurricane Camilla waves due to like this like the wave induced the seafloor failure. Like is showing here, the soil failure zone is about 100 feet, like deep, like the thick, and also causing this mud slide. So imposing the structure loading on the platform. So causing the pile fail at the base of the jacket. Basically like the platform was toppled over. The hurricane wave, like basically like this, like the wave bottom pressure can cause the cyclic kind of sediment movement and also like the soil, like the failure zone. So as mentioned before, it can cause slope failure of some mud flow lobes. So this one shows like the example of the desktop study we performed. So we first performed the wave propagation analysis. So from this analysis, we can produce the wave height period spectrum during the hurricane peak hour waves. And also from the wave seabed interaction study, we analyzed the sediment like motions caused by the seafloor failure, like including the sediment horizontal movements, vertical movements, the cyclic strain. So basically, as it's showing here, so for this one, we have this soil failure zone up to basically 8 meters with significant cyclic shear strain level. So after we get the sediment motion profile, when we do in the foundation design, incorporation of the mudslide like effector, so similar as previous gas hydrate, like the Wilbur soil stability analysis. So because of the soil motion, the additional structure loading going to be caused and imposed on the foundation elements. So the foundation elements for the design, we need to consider this additional loading. So here, instead of the soil to provide soil resistance, the soil going to kind of impose cyclic soil loading on the structure on the pile here. So for the foundation design, this is the specific point that we need to like take account of. Okay, and the last but not the least, the example is the effect of seismic fault intersecting offshore production well. So basically, fault, like typically fault we saw very common is like the seismic faults to causing the earthquake like motion. So in offshore, like the deep water environment, we also see very common is what we call the seismic fault. Sometimes we also call it like also typically called like the fault creep. Basically, it's like creep, like the soil movement. This a seismic fault, like the moving without causing a notable earthquake, characterized by steady movement of the plates along the fault line. So for the seismic fault movement, it can vary from continuous to episodic, lasting minutes to days. We in offshore, like the geotechnical engineering like field, the effect of seismic fault intersecting like the foundation facilities, like kind of like have been discussed before. One case history like study is presented by Dr. John Audibert back within his Fugro colleagues back in 2004. So in that study, there has a seismic surface growth normal faults intersecting with the TOP pile in Gulf of Mexico. Now it's called the Gulf of America region. So in that study, they were using like the beam column analysis to analyze the lateral deflection and the shear force on the pile due to this active like the surface growth normal fault movement. So in this current study, we actually analyze a seismic fault intersecting with a production well. So we, instead of using beam column analysis, soil spring, we employed a finite element like tool, Praxis 3D, to assess this seismic surface fault intersecting effect. The site is also at the Gulf Mexican site. It's like the all clay profile, basically at a significant like the subsurface below mudline. So as mentioned before, for the Praxis 3D numerical simulation, the wheel casing is simulated as an embedded beam structure element. The fault slip surface is modeled as a discrete interface element accounting for the weakened strength of the fault zone sediment. So for the analysis, we actually evaluate the effect of sediment on the shear strength. So as shown here, not surprisingly, when the sediment strength it's stronger, because it's similar as previous discussion about with the mudslide study and also gas hydrate dissociation wearable stability study, because here the soil movement actually imposing loading on the structure. So when sediment has a stronger shear strength, we can actually see higher the response within the wheel casing. So we are observing higher great bending moment and also larger shear stress, higher the horizontal displacement of the wheel casing. Similarly, we also investigate the soil stiffness impact on the structure response. So yeah, also similar as the previous conclusion, when the soil has a stronger stiffness, larger stiffness, the impact it's more significant. So we are saying the higher bending moment, similar as the previous, larger horizontal displacement. We are also investigate the fault displacement. So so here you can see when we have a larger fault movement, actually it's going to cause the bending moment higher than the steel yielding moment. The plastic deformation going to occurring in the casing. So basically the casing going to be overstressed. We also investigated the scenario whether this fault is it's like the localized fault or it's like a laterally widespread fault. So as shown here, the analysis indicate for these two scenario, there is a very minor. Basically, it's kind of unnoticeable difference in terms of structural response. Also, like we also investigate the numerical like skin, whether we simulate the fault as a fault slip zone, or we just like kind of like consider in the numerical analysis as a kind of like slip, kind of like the interface element. So as showing here, so if we consider like the in the numeric, if we consider like the fault, it's a fault slip zone with like the finite thickness about 0.5 meter here, in comparison with we using the interface element to consider it just kind of a slip area, the structure response are different. So the finite slip zone basically going to cause more severe structure response consider if we just using interface elements, the case. Also here, like for the finite thickness, we actually consider 0.5 meter. It's based on like the published literature study. It's indicated the average fault zone width is in about tenths or hundreds of centimeter or more. So this reason, like in the desktop study, we adopt a 0.5 meter like the zone thickness. So the previous analysis, sensitivity analysis indicated it's very important to have a good understanding of the site condition, including the soil shear strength, stiffness parameter, and also to utilize a reasonable modeling approach so we can get a realistic kind of numerical simulation results to quantify the effect of the seismic faults intersect with like the facility. Yeah, so here basically summarize the these 4 case studies I wanted to introduce today. Yeah, due to time strain, like basically each study we just briefly touch on. Yeah, if you wanted to know more details, yeah, we can certainly talk more offline. Yeah, yeah. And once again, thank you for your time. Yeah, thank you.
Great stuff. Okay, thank you. I appreciate that, Xiaojiang Long. Really a great, interesting presentation. So for our viewers, if you do have questions, go to the Slido link, use the code #studies and drop your questions in there, and Dr. Long can answer them. So maybe the first one is, of all the case studies that you shared today, which geotechnical challenge proved the most difficult to resolve and why?
Yeah, I think basically, I think all these 4 case studies we're showing here, they are impose kind of unique challenges. So for example, like gas hydrate analysis, I mean, like so first, like for the hydrate study, like the difficulty is like as engineering analysis. First, how to characterize the nature of the hydrate. So basically, like here, like for this project, we have to utilize like the seismic inversion, like based on the geophysical kind of like the amplitude to kind of to estimate what are the hydrate saturation profile and also the geothermal gradient, and also like the study also needed to have a good understanding of the petroleum engineering, to understand what is like the procedure of in terms of the wellbore installation, like the casing structure, So these are actually like kind of like to all call for like what we call the interdiscipline kind of studies, not just focus on the geotechnical engineer itself. So we need to have a broad understanding as a teamwork to work together with the geoscience team, with like the client, like the petroleum engineer, drilling engineer. So to have a thorough understanding of what actually happened in the field, and also as showing here. So sometimes we don't have a textbook established solutions. So for the problems, we will have to basically based on our kind of like the soil mechanics, like the structure, like the foundation engineer, like analysis kind of background. But we have to kind of sometimes thinking out of box, kind of to as here showing. So we have to kind of to propose like two different scenarios, kind of a bonding conceptual model, because try to cover the uncertainty in the field. So like I would think so this is an example of the hydrate study, and for the hurricane for this mudslide, like the hurricane wave is also another example. It's also for the multidiscipline. So we need to understand working closely with Meta Ocean, like the engineers to understand the wave loading, wave pressure, kind of. So like I think among the four examples, so basically this jackup rig, like spudcan penetration induction, these are more falling in the traditional category of the geotechnical engineering, but this one is kind of like more, this is, it's very kind of technical challenging because we have to utilize a battery of application analysis, ranging from traditional small strand fundamental element to kind of couple the Eulerian, like like a large deformation analysis. So yeah, so I mean these four are I think are kind of an example I want to present is because it kind of give a message showing like as a marine geotechnical engineer, sometimes we need to think out of a box to know how to simplify the problem and also to know how to work effectively with other interdiscipline, like other like lines of engineers, like Meta Ocean, geophysicists, the geoscientists, petroleum structure engineer. So everything kind of is because for project is a teamwork. So yeah.
Great stuff. Yeah, great. Thank you for that one. Next question. How do you balance analytical modeling with limited field data when dealing with complex and uncertain seabed conditions?
Yeah, I think this is a very, very good question. So basically, this is always we kind of struggling with the project, especially if the project calls for kind of advanced complex numeric modeling. So the complex modeling often has lots of input parameters requirement, sometimes even more than 10. So how to effectively kind of get a good realistic kind of this input parameter based on limited kind of geotechnical data, it's always a challenge. So this reason, like most of the time, we actually perform sensitivity studies. So we acknowledge the limitation of the limited data, and then like we first identify what are the most controlling parameters, and among these controlling parameters, we may based on our experience, judgment, and also the available data, and also sometimes the past past experience working in the region is also very important. So we incorporate all these. Then we normally give a sensitivity study, so give a range. So kind of give a client a scenario, what is the worst scenario, what is the most optimal scenario. Yeah. So sensitivity studies is very, very common we perform to try to capture the uncertainty due to this limited field, like geotechnical data available. Yeah.
Great. Okay, thank you for that. And to our viewers, please drop questions into Slido, and we'll answer them. Next question. Looking ahead, what advances or tools do you think will most improve how the industry manages offshore geohazards?
I'm sorry, can you say one more time?
Yeah, sure.
What
Looking ahead to the
Uh-huh.
future, what advances or tools do you think will most improve how the industry manages offshore geohazards?
Yeah, I think basically this is we are in the age of like the technology advancement. So I would say like the innovation is a key. So so one thing, one example here showing like the gas hydrate for the gas hydrate analysis. So basically we utilize the like the seismic inversion. This basically is also kind of recently like advanced tool in for the geohazard integration study. Also, like we talk about using machine learning kind of things to try to based on kind of like the sometimes based on like the certain part of the data set that we can explore to get a pattern to try to get like the more like effective kind of application. Yeah, I would say like the and also in terms of like for example like the offshore like renewable geophysical survey. Now people talking about like the like from the high resolution to ultra high resolution. So try to get more like the coverage and with more like the resolution requirements to fit for the facility for the design needs. Yeah, so I think like the innovation is always a key. So we need to kind of to employ it in offshore like the um offshore engineering and also the geohazard like basically in many aspects. Yeah.
That's great. Yeah, okay, thanks for that response. Another one, with these complex models that you shared with us today, particularly the CEL model, how do you ensure the results are correct, and how do you validate such a complex model?
Okay, I think this is a very good question, a great question. So basically, like due to the time limitation, I didn't touch on the detail. So for the spudcan penetration, the CEL analysis, before we perform this CEL analysis, we actually conduct kind of like the spudcan penetration analysis based on a classical kind of like the bearing capacity, like specified in the SNAIM like a guideline. So based on the site condition and also the SNAIM guideline, like the formula, ISO formula, we have predicted the spudcan penetration like the curve. So we use that curve as sort of a benchmark to verify the efficacy CEL analysis. So like so the first step like we compare the CEL analysis results with our like the classical kind of like bearing capacity theory, like the spudcan penetration analysis results. And when the results are pretty are matching very closely, I think for this study, they are matching about like I think the difference is less than 2%. So basically, so we have a very good like confidence in terms of the numerical accuracy of the efficacy CEL analysis. Yeah, this is a very good question because every numerical analysis, I mean, numerical analysis is sometimes it's a black box. So we need to make sure like the input parameters are correct, like also the output results like are matching with the physical mechanism, and also we need to like the benchmark basically from the classical solution. So this way we can make sure it's not a kind of the numerical accuracy.
That's great. Okay, thanks for that. And this is the last question here on Slido. For anchor piles serviced beyond the original design life and being considered for life extension, what types of engineering assessments are required to validate its integrity?
Okay, so basically for this life extension type of project, we typically involve it's kind of like to assess the holding capacity, and also like sometimes like for the fatigue life also to assess. So for one example is like in typically traditionally for Gulf of Mexico, like when we do the jacket pile design, we normally follow the API approach. But like the API, as we all know, API soil spring is typically pretty conservative, like on the soft side. So after like for example, after 20, 30 years design life, and also like the in the API, like the holding capacity, like formula standard actually is not the ultimate holding capacity. It's like the corresponding to the pile loading test at certain days in the field when the API kind of guideline was formulated. So we actually based on the like one type of work we normally do is like for the pile aging, kind of due to the aging effect. So the pile actual holding capacity actually it's higher than what stated in the design report based on the API standard. So for due to this pile aging like mechanism, like the actual pile capacity actually could sometimes even 50% more. So the pile's design life can certainly be extended from the specified, for example, 30 years. And also another thing you need to also verify is for the fatigue life. Yeah, and but normally for the fatigue design, like we also have a very good factor of safety built inside also. So basically, so sometimes it's over conservative. So with all this considered like the life extension, it's kind of like to extend the pile design life is always it's like it's like sometimes it's kind of it's feasible, so the client can utilize the pile, yeah, more than the design life.
Great stuff. Okay, thanks for that. Okay, we'll begin to wrap up the meeting now. So, firstly, I want to thank our speaker, Dr. Xiaojiang Long, for a well-delivered presentation this morning, and also would like to thank Fugro, the IMarEST, and 2H Offshore. Also with this, we want to thank all of our global viewers who are able to find the time to join us today for this webinar and for asking the questions. So we do appreciate that. In terms of continual professional development, the IMarEST does offer a CPD certificate to all viewers that attended this webinar. So if you did attend, you should receive that via email in the next few days. If you'd like to kind of hear more about the special interest group or would like to propose ideas for the special interest group, then please reach out either to the chair of the SIG, that's Dr. Nimi Albili, or to myself, and we'll try and help there. But we do need input from listeners like you so that we can add value. The next webinar topic, it's going to be called Recognizing Your Hidden Obsolescence Risks. It's a webinar by the Offshore SIG from the UK, and that's going to be on November the 19th at that'll be 4 p.m. UK time or 10 a.m. Central Time in the US. So this now brings the webinar to an end. Thank you for joining the IMarEST Oil and Gas Special Interest Group today. We look forward to having you on our future webinars, and do have a great remainder of the day. So thank you.
Yeah, thank you.